Yes, ladies and gentlemen, welcome back. Thanks for another vote of confidence. Remember to like if you like. If you don't like, well, I don't know what you're doing here. You obviously want to stay with us because you like what we're trying to do for you. Now, let's look at the operational amplifier today, the op amp in short. Why do we have the op amp? The op amp is basically it is actually an integrated package of our bi-junction transistors, our PNP, NPN transistors put together, because for as individually, okay, they have instances where they are adequate and whatever, but there are instances where we need vast amounts of amplification, where we need serious levels of amplification, where the BJT just does not cut it. So what do? We put them together and cascade them, you know, and we work out, we try to cut off all the individual weaknesses, so that in a package, in this IC huge package, we end up with this amplifier with one giant amplifier. It is actually an IC. It is not appropriate. I'm not happy when it's called a component, because it is a component, if you want to say, but it is a component made up of hundreds of other components. You know, these it is basically circuits. All right, it is basically circuits, so it is an integrated package. All right, but anyway, why did we like I said, because the BJTs are the bi-junction transistors are actually a little bit limited in terms of amplification. We decided to say, okay, how do we then help make them help each other, you know, cascade them and make them help each other to make their effort much more robust. And what do we say? We say, okay, this is actually a design. Okay, they didn't just fall like manna from heaven. This was a design. So what did we design them to do? The op amp was ideally designed to possess a few properties, and those properties will be infinite open loop voltage gain, meaning that we want to have as much gain from this as possible. Why open loop? Because if it's closed loop, then we determine the level of amplification. But in open loop format, you will see that the amplifier it is designed to have infinite voltage gain. It is also designed to have infinite current gain there, again with the open loop. Because remember to say, what do I mean by open loop? In this format where I just take an amplifier as it is, where I take the the op amp as it is, and I just give it inputs without taking feedback back to it, without giving it feedback, taking outputs to feedback. That would be open loop. That's what you mean by open loop. Now, remember, open loop means no feedback, all right, whereas closed loop means with feedback. All right, so open loop, the current gain is also very massive. Actually, by design, it is infinite. All right, we also designed this guy to have input impedance that is infinite as well. Why do you want a high input impedance? Why do you want an infinite input impedance? We do not want this guy to start amplifying noise, for instance, unwanted signals, you know. So we designed this guy, the op amp, to have such a massive input impedance. By design, actually, again, it will be infinite, unlimited, all right, so to speak. So you interchangeable. You could say unlimited, you could say infinite. I mean, I believe those two words are synonyms. They are synonymous. All right. So now we also design our op amp to also have zero output impedance. That is by design. We design it to have zero output impedance. But then now, why would we want to have zero output impedance again? We don't want our amplifier to impede our output. We want our output to come out freely. So by design, it should have typically what I would call, I want to take this up a little bit. I can see that I'm gonna be struggling for space here. All right, I'm gonna be struggling for space. We'll bring this back. So we are, by design, we want this to have what? Infinite bandwidth, meaning that it should be able to handle different from DC to all the way to what to any frequency. All right, so we should have an infinite bandwidth. There should be no limitation as to what size, what frequencies we can work with when it comes to what, to an to amplifiers, you know. So now we also want to have, when you talk, oh, what have I done? Moved it back. I've moved it back. I wanted to add another property which will be the null set, the null offset voltage. The null offset voltage. When I feed nothing onto the op amp, I want that op amp to give me nothing. If I give it zero input, then I want it to give me what call this nothing. I don't want without any input to have some voltage. That is what we call offset. We do not want to have an output when there's no input that's meant to give us anything. All right. So when our input voltage is zero, then our output voltage should also be zero. That is the design. That is what we would like to get with the what, with the operation. Unfortunately, my picture is in the way there. Hopefully I'll take it a bit later. I had to make my notes to avoid the lots of writing while I'm explaining what I have to explain here. Now, so by design, I'll so, however, this was the design. What did we then achieve? It means even though our plan was to get this perfect amplifier that would do all these things, but in practice it was a little bit impossible. It's impossible to design anything. This is what we call the ideal op amp. Ideally, the op amp should have these properties, all right? But then in practice, well, we wanted to have infinite infinite open loop voltage gain, infinite open loop current gain, infinite input impedance. Okay, we wanted to have I should have said here actually Z in is equal to infinity. All right, I should have said here Z in is equal to infinity. That was our design here. Okay, and our Z out is equal to 0. We should have no output impedance whatsoever. Again, I repeat, our output should be able to flow freely out of the amplifier. All right. So then, however, we also intended to have infinite bandwidth, as I've already said, and also zero offset voltage. But what happens in reality? We do not have anything. You want a perfect companion, but you've got the person you have, right? So instead of infinite voltage gain, what did we achieve in real life? I will actually put red so that we remember. We actually got very high instead. Very high, all right. In the region of what? In the region of 100,000, 200,000, in the hundreds of thousands, all right. In the region of 100, I would say safely around 100,000. So instead of what? AV is plus minus 100,000. Okay, we didn't really get to have the infinite voltage gain that we ideally had. We also have, instead of achieving infinite open loop current gain, we also got very high. You will realize that we didn't really fall far off because this was our design. If you aim high, you always get close to your aims. Now, you might not get exactly what you wanted. That is why when you're going for a test, don't aim for 50%, because if you don't get you don't achieve that, it means you fail. So if you aim for a distinction, if you aim for 100%, then you might not get 100%. You just as well might. But if you don't, probably you get yourself a good distinction. All right, aim for a distinction, and you probably be in the the high figures. All right, but aim for a pass rate. Good luck then. All right. We wanted to achieve infinite input impedance, all right, but we did not get that. You will see that all these infinite values are actually replaced in the practical by very high, not infinite, but very high. All right, input impedance, all right, that will be in the region of 1 meg. All right, this is typically in the region of plus minus 1 meg, plus minus 1 mega ohm. All right. So as for output impedance, yes, we would like to have 0. Our design was to have 0, but unfortunately, no, we do not have that. We have it in the region of, obviously, the opposite of very high would be very low. All right, acceptably low. If we really failed dismally, we wouldn't worry about it, would we? So it was acceptably low, very low. Instead of 0, is very low, typically around plus minus 150. Typically plus minus 150. All right, that is very low. It is not ideal, it's not 0, but it's definitely not huge. It don't fall in the huge category, right? Also, with the frequency. Okay, with the frequencies, these op-amps did not really attain infinite bandwidth, but at least the range of frequencies is very wide. The bandwidth is wide, so this will be a very wide bandwidth. Instead of an infinite one, we still fell within reason, and this was a very wide. All right, so be very careful what you ask for. And also here, instead of 0, obviously now you would see the pattern. We actually got low, right? Low, very low. Instead of 0, very low. All right, low offset voltage. All right, so now typically you would be asked to either provide, typically you'd be asked to provide the ideal properties. Okay, I'm still having the wrong tool. Okay, so typically you'll be required for ideal properties, in which case you have to say what the design properties were. All right, but if you ask for the practical, so be careful what you ask for. If you ask for the practical properties, then you have to say what we got. You wanted an angel, but you've got the lady or dude that you have, man. So that's your angel. That's your angel, right? So we couldn't get ideal, but at least we didn't fall too far, because we aimed high, we didn't fall too far. So we are going to go on next and go into the what, into the. I cannot deal with the op amp in one go. All right, that will be a very lengthy video, so I'll break it here for now. I'll come back and explain exactly how this or what call this operational amplifier works. So hopefully that was not bad. So sign off. Remember, if you like, it's better to subscribe, because every time we release something for you, if you like us, if every time we release, we give out something, you'll be the first to know. All right, then, till we meet again, dealing more with the op amp. All right, later.